For as long as humanity has existed, we have looked up, searching for meaning in the scattered lights that pierce the dark. Those pinpricks, so distant and untouchable, have guided our myths, our calendars, our ships, and our dreams. Yet for most of human history, the heavens were a mystery, a vast and silent ocean beyond the reach of our sails. That ocean has never stopped calling. In the 21st century, we are witnessing the most extraordinary transformation of human curiosity since the invention of the telescope. What began as questions whispered by ancient astronomers, "What are the wandering lights in the sky?" has become a planetary-scale endeavor to uncover the truth of our origins. We have left footprints on another world, sent metal emissaries into the cold black between the planets, and turned our cameras outward to glimpse the shores of alien landscapes. But behind every image of Mars, behind every mosaic of Saturn's rings or the blue marble of Earth, lies something deeper, a story of connection. Because to understand the worlds beyond our own is to understand ourselves. Our journey begins not with rockets or computers, but with a spark, the same spark that drew early humans to paint the stars on cave walls. They saw patterns in the night sky, hunters, lions, goddesses, heroes, and believed that fate itself was written among them. They were right in a way. The atoms that make up our bones and blood were born in stars long dead, scattered by ancient supernovae and gathered by gravity into this small, blue planet we call home. Now, as we stand on the threshold of a new era of exploration, the questions grow larger, not smaller. What forces shaped the planets that orbit our sun? How did life take hold on one, and perhaps only one of them? And if the same cosmic ingredients are scattered throughout the universe, why not life elsewhere? To search for answers, humanity has built machines of unimaginable precision. Orbiters that glide through alien skies, landers that dig into foreign soils, and telescopes that pierce through the cosmic fog to glimpse galaxies billions of light years away. These machines have become our eyes and ears, extending human curiosity far beyond the limits of flesh. Each image they send back, a crater on Mercury, a storm on Jupiter, a glacier on Mars, is a fragment of a larger story. The story of a solar system alive with motion and history. A story where planets evolve, collide, and transform across billions of years. Where frozen moons hide oceans. Where storms rage for centuries. And where, in one corner of all that vastness, a fragile species dares to wonder if it is alone. This is a journey through time and space, from the birth of the sun to the outermost edges of the solar system, where light itself grows faint. It is a chronicle of discovery, of science and imagination working hand in hand. But it is also a reflection on what it means to be human in a universe that does not know our name. Somewhere out there, beyond the glow of our own star, lie worlds of fire and ice, ancient, alien, and astonishing. Worlds that hold the memory of creation itself. And so we begin, as explorers always have, by looking toward the horizon and asking the oldest question in existence. What lies beyond? Part 1, The First Light. When humanity looked up before the first telescope was built, before the first map of the heavens was drawn, there were the Watchers, men and women who stood under the night sky and searched for meaning in its endless rhythm. They had no machines, no equations, only eyes and imagination. Yet they noticed something astonishing. The sky was alive. Night after night, they watched the constellations drift slowly westward, the moon wax and wane, and certain bright points wander across the heavens in strange, looping paths. These wanderers, as the Greeks called them, planets, were the first clues that the cosmos was more than a backdrop. It was a system, a clock, a mystery in motion. To the ancient Babylonians, the heavens were an oracle. The Egyptians aligned their temples with the rising of Sirius, heralding the annual flood of the Nile. In the Americas, the Maya carved entire calendars into stone, counting the precise cycles of Venus. Across continents and millennia, humanity discovered that the universe was not chaos. It was patterned, ordered, and perhaps intentional. But there was something else. something that haunted every civilization that gazed upward. Among the fixed stars, there were disruptions. Comets with blazing tails, sudden eclipses that turned day into night, mysterious lights that appeared and vanished. The sky was not constant. It was capable of change. Change meant possibility. When Galileo Galilei first turned his handmade telescope toward Jupiter in 1610, he was not simply making an observation. He was rewriting the human place in the cosmos. Through that small, trembling lens, he saw four tiny points circling the giant planet. Moons, worlds orbiting another world. It was a revelation so profound that it shattered the foundations of philosophy and faith alike. If Jupiter had moons, perhaps Earth was not the center of all things. Perhaps the heavens were not perfect and immutable. Perhaps we were not unique. From that moment, exploration became inevitable. The telescope was the first great leap, a bridge between the human eye and the infinite. With it, astronomers began to see the universe as a landscape rather than a mystery. The planets ceased to be divine symbols and became destinations. Mars showed dark markings that hinted at continents and seas. Venus revealed a thick veil of clouds. Saturn displayed its impossible, delicate rings. Every discovery raised new questions. What are these worlds made of? Could they harbor life? And if so, what kind of life could exist beneath alien suns? For centuries, the answers lay beyond reach. Humanity's view of the solar system was trapped by distance, by the thin shell of air that cloaked our world and blurred our view of the stars. But knowledge is restless. Curiosity is relentless. In the 20th century, that restlessness took on the shape of fire. Rockets, once weapons of war, became the vessels of exploration. The roar of combustion replaced the quiet hum of telescopes. For the first time, we were no longer looking at the cosmos from afar, we were entering it. When the Soviet probe Luna 3 sent back the first images of the moon's hidden far side in 1959, humanity caught its first glimpse of an unseen world. It was gray, cratered, desolate, and breathtaking. In that grainy photograph was something monumental, proof that we could reach across space, if only with machines. A new era had begun. The watchers of old had read omens in the heavens. The scientists of the modern age were learning to read data, streams of numbers and light, signals whispering across millions of kilometers. The universe was beginning to speak, and for the first time we could listen. Yet even as we turned our gaze outward, a deeper question emerged. If every planet is unique, what makes Earth so different? In the cold light of space, our world is just another sphere of rock and gas orbiting a star. And yet, within that fragile balance of sunlight and atmosphere, oceans and gravity, something extraordinary happened. Life. The story of how that life came to be, and why it flourished here and perhaps nowhere else, is written not just in our rocks and oceans, but in the planets that share our sun. To understand ourselves, we must understand them. The first light we saw in the sky guided us toward that understanding. It was the beginning of science, of curiosity, of destiny. And as the night sky continues to unfold before our instruments and eyes, we are still the same watchers, standing beneath the stars, asking not just where we are, but why we are. Part 2. The Age of Discovery. Eyes in the sky when humankind first stepped beyond the cradle of Earth. It was not with a whisper, but with a roar. The age of telescopes had shown us distant worlds as points of light. The age of rockets would transform them into places, destinations waiting to be explored. The year was 1957 when a metallic sphere the size of a beach ball rose on a column of flame and changed history. Sputnik 1, the first artificial satellite, orbited the Earth for just 3 months. It was little more than a radio transmitter, yet it carried with it a message more powerful than its signal. The sky was no longer beyond reach. In the years that followed, space became the new frontier of human ambition. The Soviet Luna missions reached the moon. America's Mariner probes flew past Venus and Mars. Each mission was a step away from the dream of astronomy and toward the reality of exploration. And then came the moment that would redefine what it meant to be human. 1969. The Apollo 11 lunar module descended toward the gray dust of the Sea of Tranquility. Millions watched on television as Neil Armstrong's boot pressed into alien soil. For the first time, humanity was no longer confined to Earth. That small step was not just a triumph of engineering, it was a triumph of perspective. From the lunar surface, astronauts looked back and saw the Earth rise above the horizon, a glowing blue marble hanging in a black void. Fragile, finite, alive. The photograph known as Earthrise became one of the most important images ever captured. Not because it showed the moon, but because it showed us. For centuries, we had imagined ourselves as the center of creation. Now we saw the truth. Our world was small and it was shared. But the moon was only the beginning. The real revolution was happening farther away, beyond the reach of human footsteps, carried by the machines we built to be our eyes in the sky. In 1973, Pioneer 10 crossed the orbit of Mars and became the first spacecraft to journey toward Jupiter. It carried a gold plaque engraved with a map of our solar system and a simple image of a man and woman. A cosmic message in a bottle, adrift among the stars. Behind it came Voyager 1 and Voyager 2, twin explorers launched in 1977 on a grand tour of the outer planets. They visited Jupiter, Saturn, Uranus, and Neptune, sending back images that redefine the way we see our solar system. Storms larger than Earth. Rings that shimmered like glass. Moons with volcanoes and icy fissures that hinted at hidden oceans. Each transmission from the Voyagers was like a postcard from the edge of the unknown. Humanity was no longer guessing what other worlds looked like. We were seeing them with our own eyes. As technology advanced, our view sharpened. The Hubble Space Telescope, launched in 1990, lifted our gaze from the planets to the stars themselves. Free from the distortions of Earth's atmosphere, Hubble revealed galaxies colliding, nebulae glowing with newborn stars, and the faint light of the universe's earliest moments. What had once been faint smudges of light became windows into cosmic history. But perhaps Hubble's most powerful image was again one of humility, the pale blue dot. In 1990, as Voyager 1 left the solar system, scientists turned its camera back toward home. From billions of kilometers away, Earth appeared as a single pixel, a fraction of a frame, suspended in a sunbeam. Carl Sagan, one of the mission's architects, said it best, "Look again at that dot. That's here. That's home. That's us." The age of discovery had transformed us. Once, the stars were gods. Then they became distant suns. Now, they were laboratories, places to study, to measure, to understand. Yet every new answer brought deeper questions. Why did our solar system form the way it did? Why are some planets frozen and lifeless, while others, like Earth, teem with oceans and life? And what, if anything, connects them all? The next generation of missions would seek to uncover those mysteries, not from afar, but up close, with orbiters circling planets, rovers crawling across alien deserts, and landers digging into the soil of other worlds. It was time to go beyond looking. It was time to touch. The cosmic explorers, Mariner, Viking, Voyager, Hubble, had opened the path. Now, new emissaries would follow, carrying humanity's questions into the dust and storms of the solar system. Each discovery would bring us closer to understanding a fundamental truth, that the same forces which shaped the planets also shaped us. That the story of the solar system is, in the end, the story of Earth and of life itself. The eyes in the sky had shown us the way. Now, the journey inward, into the heart of our cosmic neighborhood, was about to begin. Part 3. The Birth of Worlds. The solar system takes shape 4.5 billion years ago, before there were planets or moons, before the sun itself began to shine. There was only dust, a vast, silent cloud drifting through the arm of our Milky Way. It was not a special place. Countless such clouds fill the galaxy. But something stirred here. Gravity, the invisible sculptor of the universe, began its slow, relentless work. Tiny particles of ice and minerals collided and clung together, forming clusters. Those clusters grew into boulders, then mountains, then worlds. As they gathered, Their motion created heat. And at the center of this storm of dust, pressure built until hydrogen atoms fused into helium, and a star was born, our sun. It blazed to life with such intensity that it swept away the remaining gas and dust in a great solar wind. What remained behind was a flattened disk, a cosmic workshop where the raw materials of creation assembled themselves into planets. The story of our solar system began here, in that swirling ring of chaos, close to the newborn sun, where temperatures were scorching, only metals and rocky materials could survive. Here, the small, dense worlds of Mercury, Venus, Earth, and Mars took shape, terrestrial planets, built from the heavy elements forged in ancient stars. Farther out, beyond the line where sunlight no longer melted ice, a different kind of planet was born. Jupiter, Saturn, Uranus, and Neptune formed in the cold, massive enough to trap the light gases hydrogen and helium, becoming giants wrapped in thick, turbulent atmospheres. Between them lay remnants, the leftovers of creation, asteroids, comets, and icy fragments that never grew large enough to become planets. Yet those fragments carried the ingredients of life itself: carbon, oxygen, nitrogen, and water. They were the seeds from which the Earth would one day bloom. For hundreds of millions of years, the young solar system was a place of unimaginable violence. Planets collided, moons were torn apart and reformed, asteroids bombarded every surface. The scars of that chaos are still visible today. In the craters of the Moon, the ravaged plains of Mercury, the broken rings of Saturn. Out of that cosmic war came a strange balance. Earth emerged from the fire as a sphere of molten rock, glowing like a brand. As it cooled, volcanoes released steam and gases, forming the first atmosphere. Water, perhaps delivered by icy comets or trapped within the planet's minerals, condensed into oceans. And in those oceans, something miraculous happened. Somewhere, somehow, molecules learned to copy themselves. Chemistry became biology. In the grand clockwork of the solar system, a single planet began to dream. The rest of the system, meanwhile, evolved along its own paths. Venus, Earth's twin in size and mass, became a furnace under the crushing weight of carbon dioxide. Mars, smaller and colder, lost its atmosphere and dried into rust and dust. Jupiter grew so massive that its gravity dominated the entire outer system, shaping the orbits of worlds and shepherding the debris that might otherwise have struck Earth. In time, each planet would come to tell its own story, but their origins were shared, written in the same cosmic script, traced in the dust that once drifted through space. Modern astronomy has confirmed what those early patterns hinted at. With telescopes like Hubble and the James Webb Space Telescope, scientists can now watch other stars forming in the same way, surrounded by glowing disks of gas and dust, embryonic planets swirling within them. The universe, it seems, is not content to build one solar system. It is building billions. Yet our own remains special to us, not because it is unique, but because it is home. Every mountain, every ocean, every heartbeat on Earth is part of a chain of events that began in the collapse of a distant cloud. We are not merely inhabitants of the solar system. We are its children. To trace that lineage, we follow the trail of worlds. Some bear witness to creation, others to destruction. Some are frozen in time, others alive with motion and heat. Each world is a chapter, and together they tell the story of how chaos became order and how matter learned to think. Now, with spacecraft and telescopes as our tools, we can retrace those steps, from the burning heart of the sun to the icy edges of the outer dark. Each destination reveals not only what is out there, but what once was, the memory of a system still evolving, still speaking through light and gravity. This is the story of our origins, told by the planets themselves. Next, we begin where all light begins, at the center of everything we know. Part 4. The living star. Heart of the solar system, at the center of everything we know burns a star. To our eyes, it is constant, familiar. A golden disk that rises each morning and falls each night. Yet the sun is far more than a comforting light in the sky. It is a living, breathing engine, a colossal furnace whose energy defines the very boundaries of life. Everything we are begins here. The Sun contains more than 99.8% of all the mass in the solar system. Its gravity holds the planets in their orbits, its radiation warms their surfaces, and its magnetism shapes invisible storms that sweep through space. Without it, there would be no Earth, no oceans, no blue sky, and no life to wonder at its brilliance. But what exactly is the Sun? At its core, 150 million kilometers from where we stand, the temperature reaches 15 million degrees Celsius. Here, hydrogen atoms are crushed so tightly that they fuse together, transforming into helium. The process releases an immense amount of energy, the energy of creation itself. Every second, the Sun converts nearly 4 million tons of matter into pure light and heat. That light travels across space in just over 8 minutes to reach Earth, warming continents, driving winds, and powering the photosynthesis that sustains the chain of life. For most of human history, the Sun was seen as a god, the giver and taker of life, worshipped in temples and carved into stone. The Egyptians called it Ra, the Greeks Helios, the Aztecs Tonatiuh. Yet even those ancient civilizations understood something essential. Without the Sun, everything dies. Modern science has only deepened that truth. The Sun is not a static ball of fire. It is a restless, magnetic sea of plasma. Its surface, the photosphere, churns like boiling water, sending loops of charged particles arcing into space. Beneath its calm glow lie forces of unimaginable violence. Dark patches known as sunspots appear and disappear in 11-year cycles, marking regions where the magnetic field twists and tangles. From these regions erupt solar flares, explosions so powerful they can release as much energy as billions of nuclear bombs. When those flares are accompanied by coronal mass ejections, vast clouds of plasma hurled into space, they can strike Earth's magnetic field, creating breathtaking auroras and, at times, disrupting satellites and power grids. To understand this dynamic star, scientists have sent a fleet of spacecraft to study it up close. NASA's SOHO and Parker Solar Probe, along with the European Space Agency's Solar Orbiter, are revealing the Sun as a complex, ever-changing system, one whose moods ripple across the entire solar system. Through their eyes, we've seen the Sun's corona, its outer atmosphere, glowing with temperatures hotter than its surface. We've watched solar winds stream outward at millions of kilometers per hour, shaping a vast magnetic bubble that envelopes all the planets. This invisible sphere, called the heliosphere, is our solar system's shield, a boundary that separates us from the harsh radiation of interstellar space. In a sense, we do not simply orbit the Sun, we live within it. Its energy reaches every world differently. On Mercury, it bakes the surface to over 400 degrees Celsius. On distant Neptune, it is so faint that sunlight feels like twilight. But everywhere it goes, the Sun's touch is unmistakable. It sculpts atmospheres, drives chemistry, and leaves signatures of warmth and radiation across every planet and moon. Even as it nourishes, the Sun also reminds us of time. Like all stars, it is mortal. Every photon that leaves its surface carries away a tiny fraction of its mass. In about 5 billion years, the Sun's fuel will begin to run low. Its core will contract and heat up, causing its outer layers to swell into a red giant, engulfing Mercury and Venus, and perhaps Earth itself. For a brief cosmic moment, it will shine brighter than ever. And then, when its nuclear fire is spent, it will collapse into a white dwarf, a dense, glowing ember surrounded by the ghosts of the worlds it once warmed. But that is far in the future. For now, our Sun remains stable, benevolent, and alive. It is both the heart of our solar system and the heartbeat of our existence. An engine that has burned for billions of years, turning darkness into life. To study the Sun is to study power, not just physical power, but the power of connection. Every planet, every comet, every drifting grain of dust owes its dance to this one star. Its gravity choreographs the cosmic ballet. Its light reveals the stage. And though we have come to understand it as a sphere of plasma and fusion, the sun remains, in the deepest sense, a mystery, a reminder that even the familiar can still hold wonder. Beyond its radiant edge lies a family of worlds, each shaped by its light in different ways. Some are scorched, some frozen, some perhaps once alive. Together they tell the story of what happens when a star gives birth to planets. Our next step is to visit those worlds, the small, rocky ones that orbit closest to the sun, where heat and gravity wage their eternal battle. We begin with the smallest, the swiftest, and perhaps the strangest of them all. Mercury. Part 5. Mercury. The scorched world, it is a world of extremes. A planet where the sun looms 3 times larger in the sky than it does from Earth, and where a single day burns hotter than molten lead. Mercury, the innermost planet of our solar system, is both ancient and alien. It moves so close to the sun that its very existence feels improbable. A small, dense survivor of the furnace where worlds are forged. To the naked eye, Mercury appears as a fleeting glimmer, visible only in twilight, dancing near the horizon before vanishing again into daylight. For centuries, it remained elusive, too small, too close to the sun's glare for telescopes to see clearly. Even when Galileo first pointed his instrument toward the heavens, Mercury revealed little more than a shimmering dot. It wasn't until the age of spaceflight that this hidden world began to surrender its secrets. In 1974, NASA's Mariner 10 spacecraft became the first to visit Mercury. Over 3 brief flybys, it photographed less than half of the planet's surface, revealing a barren, cratered landscape eerily similar to our moon. But Mercury was no mere lunar twin. Its gravity was stronger, its surface darker, and its heart, quite literally, heavier. Planetary scientists soon realized that Mercury was composed mostly of metal. Beneath its rocky crust lies an immense iron core, making up more than 60% of its mass, a higher ratio than any other planet. By comparison, Earth's core is about 1/3 of its total mass. How did Mercury become so dense? The leading theory suggests a violent past. Billions of years ago, Mercury may have been a much larger planet. Then came a catastrophic impact, a collision so powerful it stripped away most of its outer layers, leaving behind a metallic skeleton. What remains today is the survivor of a cosmic cataclysm. Small, dense, and scarred by history, Mercury's proximity to the sun has left it trapped in a slow and peculiar rhythm. It takes only 88 Earth days to complete one orbit, yet it rotates so slowly that a single day, from sunrise to sunrise, lasts nearly 176 Earth days. This unusual spin-orbit resonance means that when you stand on Mercury, the sun doesn't rise and set the way it does on Earth. It creeps across the sky, pausing, even reversing direction before continuing on. The result is a world divided by fire and frost. On the sunlit side, temperatures soar above 420 degrees Celsius, hot enough to melt zinc. Yet, in the darkness of night, without an atmosphere to trap the heat, the temperature plunges to below -180 degrees Celsius. Metal expands and contracts, rocks crack, and the surface itself groans under the strain of endless thermal war. The Messenger spacecraft, launched in 2004, finally gave us a complete view. After 4 years in orbit, it mapped Mercury's surface in stunning detail, revealing vast cliffs and scarps that stretch for hundreds of kilometers. These ridges formed as the planet's massive iron core cooled and contracted, causing the crust to buckle. Like a wrinkled apple left too long in the sun, Messenger also found traces of volcanic plains, evidence that Mercury was once geologically alive. Long ago, lava flooded impact basins, smoothing their floors and leaving behind vast, frozen seas of basalt. The planet's battered face tells a story of both destruction and renewal. But among Mercury's surprises, perhaps the most astonishing was ice. In the planet's polar regions, deep inside craters that never see sunlight, radar images revealed bright reflections, signatures of frozen water. Somehow, even in the closest world to the sun, cold traps exist, preserving ice that may have been delivered by comets billions of years ago. In those dark shadows, Mercury holds onto a memory of its violent beginnings, and perhaps a clue to how water reached Earth itself. Mercury's atmosphere, if it can be called that, is a ghost. A thin exosphere of scattered atoms, constantly stripped away and replenished by solar radiation and micrometeorite impacts. Here, the boundary between surface and space is almost non-existent. The solar wind slams directly against the planet, sculpting a magnetic field that, though weak, is still surprisingly strong for a world so small. This magnetism suggests that Mercury's iron core remains partially molten, a reminder that even this scorched relic is not entirely dead inside. In the silence of its long days and frozen nights, Mercury stands as a monument to the earliest days of planet building, a survivor from the dawn of the solar system. Its craters, cliffs, and scars preserve a record older than life itself. To visit Mercury is to look backward in time, to see the raw material from which Earth was made. In that sense, Mercury is not merely the first planet from the Sun, it is the first chapter of our planetary story. Beyond it lies another world, one that hides behind clouds so thick that for centuries we could only imagine its surface. A world once called Earth's twin, but in truth, its infernal opposite. Next, we travel to Venus, the shrouded planet of fire and cloud. Part 6: Venus. The shrouded inferno from a distance, Venus is a vision of perfection, a brilliant beacon in the twilight sky, second only to the moon in brightness. For centuries, it was called Earth's twin, nearly the same size, nearly the same mass, and wrapped in a reflective veil of golden clouds. But behind that beauty lies a truth so hostile, so alien, that Venus stands as both a warning and a wonder. For millennia, no telescope could pierce its cover. The planet's thick atmosphere hid every feature of its surface, leaving astronomers to speculate wildly. Some imagined oceans and continents beneath the clouds, perhaps even jungles or alien civilizations. In the early 20th century, Venus was a canvas for dreams, the last paradise before the sun. Then came the probes. In 1962, NASA's Mariner 2 flew past Venus, becoming humanity's first successful interplanetary mission. Its instruments revealed a world far from paradise, one with surface temperatures near 460 degrees Celsius, hotter than the surface of Mercury, even though Venus lies twice as far from the sun. Later missions, including the Soviet Venera landers, confirmed the nightmare. An atmosphere 90 times denser than Earth's, composed almost entirely of carbon dioxide, with clouds rich in sulfuric acid. The pressure on the surface of Venus is equivalent to standing nearly a kilometer underwater on Earth. Any spacecraft that lands there is crushed, melted, or both within hours. The Venera 13 probe survived just 127 minutes before succumbing to the inferno, but in that time, it sent back the first color images from the surface. They showed a barren plain of cracked, orange rock under a dim, amber sky. No jungles, no oceans, only silence and heat. What happened to Venus? Scientists believe it may once have been a temperate world, with shallow seas and a mild climate not unlike Earth's. But as the young sun brightened, water on Venus began to evaporate. In the upper atmosphere, ultraviolet light split those water molecules apart, and the hydrogen, the lightest element in the universe, escaped into space. With its water gone, Venus lost the one thing that could moderate its climate. Carbon dioxide, released by volcanoes, built up in the air. Without oceans to absorb it, the gas trapped heat through an unstoppable greenhouse effect. The planet's surface temperature soared, turning rock into magma and air into poison. Venus became a cautionary tale, a glimpse of what happens when a world's delicate balance collapses. Yet even in its hostility, Venus remains an object of fascination. Radar mapping by NASA's Magellan mission in the 1990s unveiled a landscape shaped by vast volcanic plains, towering mountains, and circular coronae, enormous structures formed by upwelling magma. The lack of small craters suggests that Venus's surface is geologically young, perhaps less than 1 billion years old. This means that the planet may still be active. Some scientists believe Venus experiences massive, planet-wide resurfacing events. Episodes when heat trapped within bursts through the crust, flooding the surface with lava and reshaping the planet in one catastrophic sweep. The possibility of active volcanoes on Venus is not just academic. It's evidence that the planet is still evolving, still alive in its own way. In 2023, orbital observations from Venus Express revealed hints of volcanic plumes and temperature fluctuations in certain regions, perhaps signs of recent eruptions. But the mystery doesn't end with geology. Hidden high in the planet's atmosphere, 50 kilometers above the surface, where temperatures are surprisingly Earth-like, clouds swirl in hurricane-force winds. It was here, in 2020, that astronomers detected traces of a molecule called phosphine. On Earth, phosphine is associated with biological activity, produced by microbes in oxygen-starved environments. Could something, anything, be alive in the clouds of Venus? The discovery sparked debate across the scientific community. Many researchers urged caution, suggesting that unknown chemical reactions, not biology, could explain the signal. The evidence remains uncertain, but the question lingers like the planet's haze. Could life, stripped of its oceans and cast into the sky, have adapted to survive in the thin, cooler layers above the inferno? Venus forces us to confront the fragile boundaries between habitability and destruction. It shows us how a planet can begin as Earth's mirror and end as its opposite. And as our own world warms and its atmosphere changes, the lessons of Venus grow more urgent. Future missions, NASA's Veritas and Da Vinci, along with the European Envision orbiter, aim to return to this hellish world in the 2030s. Their goal, to map its surface in high resolution, analyze its atmosphere, and determine how and when the catastrophe occurred. Venus may be hostile, but it is also revealing. Beneath its choking clouds lies the story of how a planet can die, not from an external force, but from its own chemistry. And yet, in that story, we may find answers to our own. Beyond Venus, the solar wind grows weaker, and the sun's light dims slightly. There, another world awaits, a world that took a different path, one that found equilibrium instead of ruin. A world of oceans, clouds, and breath, the third planet from the sun. Our home, Earth. Part 7, Earth. The living planet from the black silence of space. Earth is a shimmering oasis, a sphere of blue, white, and green adrift in a sea of darkness. It is the only world, as far as we know, where the warmth of a star has given rise to life. From orbit, it appears serene, but beneath those swirling clouds lies a planet in constant motion, restless, fragile, and astonishingly alive. To understand Earth is to understand balance. It exists in a narrow band around the sun where conditions are just right. Not too hot, not too cold. Scientists call this the habitable zone, but that phrase undersells its miracle. The distance between fiery Venus and frozen Mars is not vast. Yet within that thin ring, something extraordinary happened. The ingredients of life, water, carbon, and sunlight, met under the right conditions, and the result was biology. Earth began, like its siblings, as a sphere of molten rock bombarded by asteroids and comets. But as its surface cooled, water condensed into oceans. Those oceans became both cradle and mirror, reflecting the sky above while nurturing the chemistry of creation below. No one knows exactly how life began, but the oldest fossils, found in Australian rocks, show microbial colonies that lived 3.5 billion years ago. They thrived in shallow seas, feeding on sunlight and minerals. Slowly, they changed the planet itself. Through photosynthesis, they filled the atmosphere with oxygen, a gas toxic to most early life but essential to everything that followed. The transformation was profound. Oxygen reshaped the oceans, the atmosphere, even the color of the sky. The Earth became a self-regulating system, a vast, interlinked web where geology, chemistry, and biology work together to maintain stability. It is this interplay that makes Earth unique. It doesn't just host life, it responds to it. From space, this responsiveness is visible in motion, the shimmer of clouds, the shifting of seasons, the pulse of lightning across continents. Beneath the surface, the planet itself breathes. Tectonic plates drift slowly over molten rock, creating mountains, splitting oceans, and recycling the crust. Volcanoes release gases that balance the atmosphere. Ice caps expand and retreat, reflecting sunlight like a planetary thermostat. The Earth is not static. It is a living mechanism, powered by sunlight and sustained by water, an engine of renewal. When the first humans saw their home from space, the view changed everything. The astronauts of Apollo 8 captured the now iconic image of Earthrise, the blue planet rising over the gray horizon of the moon. From that perspective, borders disappeared, conflicts seemed meaningless, and our world appeared for what it is: a single, fragile system adrift in an endless void. That image ignited a new consciousness. Environmental movements gained strength. Scientists began to study Earth not as isolated regions, but as a unified biosphere. The idea of Spaceship Earth, a world with limited resources and no resupply, became more than a metaphor. It was a reality. Today, we understand that balance more deeply than ever, and we see how easily it can be disturbed. Human activity has altered the composition of the atmosphere, warmed the climate, and reshaped ecosystems on a planetary scale. In a few centuries, our species has become a geological force, changing the planet faster than many natural processes can respond. In the silence of the cosmos, such change is both a testament and a warning. We have learned that life is resilient, but also delicate. The very systems that make Earth habitable, the circulation of the oceans, the rhythm of the seasons, the chemistry of the air, can shift in ways that challenge the survival of species, including our own. Yet Earth endures. From the depths of its oceans to the heights of its atmosphere, it remains a masterpiece of complexity. Even now, life continues to adapt, in boiling vents beneath the sea, in the ice of Antarctica, in the stratosphere above the clouds. Wherever there is energy and water, life finds a way. As we look outward toward other planets, Earth becomes both our reference and our hope. It shows us what habitable truly means, not merely a place with the right temperature or ingredients, but a system that maintains equilibrium through change. When we search for exoplanets in distant star systems, we are, in truth, searching for echoes of Earth, a familiar blue spark in someone else's night sky. But before we seek other Earths, we must understand our own. Because the forces that shaped it, volcanic heat, gravitational tides, solar energy, also sculpted its neighbors. Just beyond our world lies another that once may have been more like ours than any other. A planet of canyons, mountains, and ancient riverbeds. A world that may still whisper of its lost seas. Mars. Part 8. Mars. The desert of dreams in the cold, rust-colored expanse of Mars. Humanity sees not only another world, but a mirror of its own longing. For centuries, the red planet has been a symbol of mystery, fear, and fascination. It shines in our night sky like a coal ember, the fourth planet from the sun, close enough to reach, yet far enough to remain forever elusive. To the ancients, Mars was the god of war, its reddish hue reminiscent of blood and fire. To scientists, it became the most Earth-like of all other worlds, the one that might hold the secret to life beyond our own. It is, in every sense, the planet of dreams. But the reality of Mars is far harsher than imagination ever dared. It is a frozen desert, its air thin as high mountain winds, its ground littered with iron oxide dust that paints the planet in endless shades of red. The sun rises and sets on a world colder than Antarctica, where temperatures swing from a mild 20 degrees Celsius at noon to minus 120 degrees Celsius by nightfall. Its atmosphere, a fragile veil of carbon dioxide, offers no protection from cosmic radiation or the relentless solar wind. And yet, Mars calls to us. Long before spacecraft could touch its surface, astronomers believed they saw something extraordinary. Canals, vast, geometric lines crisscrossing the Martian plains. In the late 19th century, Percival Lowell mapped them in obsessive detail, convinced they were the work of intelligent beings. His maps were wrong, an illusion of optics and wishful thinking, but his dream was powerful. It transformed Mars into a world of possibility. That dream endured. In 1965, NASA's Mariner 4 flew past Mars, sending back the first close-up images, a barren landscape scarred with craters. The hope for civilizations vanished overnight, but disappointment soon gave way to curiosity. If Mars was lifeless now, had it always been so? Over the following decades, a fleet of missions, Viking, Pathfinder, Spirit, Opportunity, Curiosity, and Perseverance, revealed a world that once may have been far more hospitable. The Viking landers, arriving in 1976, performed the first experiments in search of microbial life. Their results were ambiguous, and debate still continues. But even more striking were the landscapes they photographed: ancient river valleys, dried delta basins, and mineral deposits that could only have formed in water. Water, the great sculptor of worlds. Mars, it seems, once had plenty of it. Billions of years ago, the planet may have possessed lakes, rivers, and even shallow seas. The atmosphere was thicker then, warm enough to allow liquid water to flow across the surface. The evidence lies everywhere. Winding channels that trace the paths of vanished rivers, sedimentary layers stacked like pages in a lost chronicle, and minerals that formed in wet conditions. Something happened. Over time, Mars's magnetic field weakened, perhaps due to the cooling of its core. Without that magnetic shield, the solar wind stripped away the atmosphere, molecule by molecule, into space. As the air thinned, pressure dropped, and the surface water evaporated or froze, the planet entered a deep freeze, transforming into the cold desert we see today. Yet traces of water remain. The Mars Reconnaissance Orbiter has detected vast deposits of ice buried beneath the soil and near the poles. In some regions, dark streaks appear seasonally along crater walls, possible signs of briny water flowing briefly before vanishing into vapor. And beneath the polar caps, radar readings suggest something even more tantalizing: pockets of liquid water trapped under layers of ice and dust. If true, they may represent refuges where life could still persist, shielded from the radiation above. The question of life on Mars remains open, not a myth, but a scientific pursuit. NASA's Perseverance rover, which landed in 2021, carries instruments designed to detect the chemical fingerprints of ancient organisms. It is collecting samples from the Jezero crater, a site once fed by a long-vanished river delta, to be returned to Earth by future missions. Each scoop of red dust could hold the fossilized remains of microbes that lived billions of years ago. And if they did, if life once began on Mars, then the universe itself is alive with possibility. Because if it happened twice in one solar system, it could happen everywhere. Beyond science, Mars has become a symbol of human ambition. Space agencies and private pioneers now dream of sending people there, not just to visit, but to stay. Plans are drawn, rockets are built, simulations run in deserts on Earth that mimic its landscape. The first human footsteps on Mars will be not just a technological triumph, but a philosophical one, proof that life from one world can reach another. But Mars is not gentle. Its air cannot be breathed. The soil contains toxic perchlorates. Its dust storms can engulf the planet for months, darkening the sky and freezing solar-powered machines in their tracks. To survive there will require more than courage. It will require transformation. Perhaps that is why Mars fascinates us so deeply. It is the test of everything we are, our resilience, our imagination, our longing to endure. And as we study it, we are reminded of something profound. Mars and Earth are siblings, born from the same cloud of dust, shaped by the same forces. But one became paradise, the other desolation. In their contrast lies the fragile balance of life itself. Beyond Mars, the sun's warmth fades, the inner solar system ends, and the vast realm of the giants begins. Worlds of gas, ice, and storms that could swallow Earth whole. The next world is the ruler of them all, a planet so massive that it shaped the destinies of every other. Jupiter. Part 9. Jupiter, the giant of giants in the grand architecture of the solar system, one world dominates all others, a vast, swirling colossus whose gravity shapes everything around it. Jupiter, fifth planet from the Sun, is not merely a planet. It is a presence. More massive than all the other planets combined, it is a failed star, a titan born just shy of ignition. Seen through a telescope, Jupiter is breathtaking. Its surface, if such a word can be used for a planet without a solid ground, is a churning ocean of clouds. Bands of cream, ochre, and rust encircle it in perpetual motion, sculpted by winds that rage at hundreds of kilometers per hour. Lightning flashes within the depths of its atmosphere, illuminating storms larger than entire continents. And among those tempests lies the most famous storm in the solar system, the Great Red Spot, a vortex that has spun for at least 4 centuries, perhaps far longer. It is a hurricane so vast that 3 Earths could fit across it, swirling endlessly in the planet's immense atmospheric engine. But what lies beneath those clouds? Jupiter is a world of gas and mystery. Its upper atmosphere is composed mostly of hydrogen and helium, the same ingredients as the Sun. As you descend, pressure and temperature rise to unimaginable extremes. Hydrogen, normally a gas, is crushed into a strange metallic form, a sea of liquid metal that conducts electricity and generates Jupiter's colossal magnetic field. That magnetic field extends millions of kilometers into space, trapping charged particles and creating lethal radiation belts. If Earth's magnetosphere were a soft hum, Jupiter's would be a thunderclap. It is so vast that if it were visible to the naked eye, it would appear larger than the moon in our sky. The planet's gravity, too, exerts a profound influence. In the early solar system, Jupiter acted as both protector and destroyer. Its immense pull deflected countless asteroids and comets away from the inner planets, shielding Earth from many catastrophic impacts. But it also hurled some inward, delivering water and organic materials that may have seeded life. Without Jupiter, the story of Earth might have been very different. Orbiting this giant is a miniature solar system of its own, at least 95 known moons, each unique, each with its own story. Among them are some of the most fascinating worlds ever discovered. Io, the innermost moon, is a place of constant violence. Tidal forces from Jupiter's gravity stretch and squeeze it like a rubber ball, generating heat that fuels more than 400 active volcanoes. Its surface is a hell's cape of molten lava, sulfur plains, and towering plumes that rise hundreds of kilometers high, a living testament to the power of gravitational energy. Farther out lies Europa, a world of ice and silence, but perhaps not lifeless. Beneath its frozen crust, scientists believe there is an ocean of liquid water kept warm by tidal heating. The evidence comes from magnetic measurements and geyser-like plumes seen erupting into space. If confirmed, Europa's ocean would contain twice as much water as all of Earth's seas combined, and where there is water, there may be life. Then there is Ganymede, the largest moon in the solar system, even bigger than Mercury, and the only moon known to have its own magnetic field. Beneath its icy surface, too, may lie a deep ocean. And Callisto, the outermost of the major moons, is ancient and cratered, a frozen relic that has changed little since the birth of the solar system. Together, these 4 moons, Io, Europa, Ganymede, and Callisto, form a family as complex and dynamic as any planetary system. Galileo first observed them in 1610, proof that not everything revolved around Earth. Today, they remind us that even in the shadow of a giant, worlds can thrive. Jupiter's influence reaches farther still. It commands the Trojan asteroids, 2 vast swarms of rocky bodies that share its orbit around the Sun. These remnants of the early solar system are time capsules, preserving the materials from which planets were made. NASA's Lucy mission, launched in 2021, is now on its way to explore them, a journey into the ancient memory of creation. And then there are Jupiter's auroras, shimmering rings of light encircling its poles, far more powerful than those on Earth. They are caused not only by the solar wind, but by the planet's own magnetic field and the charged particles spewed from Io's volcanoes. In ultraviolet light, they glow with an intensity that defies imagination. A constant reminder that Jupiter is not merely a planet, but a dynamic, living system of energy and motion. Yet for all its grandeur, Jupiter also holds secrets that remain unsolved. Does it have a solid core, or does its interior blend seamlessly from gas to liquid to metallic hydrogen? How deep do its winds go? What drives the mysterious changes in its great red spot? NASA's Juno spacecraft, orbiting the planet since 2016, is slowly unraveling those mysteries. It has mapped Jupiter's magnetic field in exquisite detail, revealed its polar cyclones, vast geometric storms, and hinted at a fuzzy, diluted core that blurs the line between solid and fluid. Each new discovery deepens our understanding not just of Jupiter, but of all gas giants, and of how planetary systems form. For if Jupiter shaped ours, perhaps similar giants shape countless others across the galaxy. Beyond Jupiter, sunlight begins to wane into twilight. The air grows colder, the distances wider. There, in the dim reaches of the solar system, another world of beauty and complexity awaits. A planet encircled by rings so delicate they seem spun from light. Saturn. Part 10. Saturn. The Lord of the Rings among all the worlds in our solar system. None captures the imagination quite like Saturn. It is the jewel of the night sky, pale gold, serene, encircled by a system of rings so magnificent they seem unreal. Through a telescope, Saturn appears not as a distant sphere but as a revelation, a planet that wears its history for all to see. Saturn is the second largest planet, yet it is the least dense, so light that, if placed in a vast ocean, it would float. Like Jupiter, it is composed mainly of hydrogen and helium, a remnant of the primordial nebula from which the Sun was born. But unlike Jupiter's turbulent, vividly colored atmosphere, Saturn's clouds are soft and muted, pastel bands swirling in slow, elegant motion, veiling a complex world beneath. Beneath those golden clouds lies a giant of layers. Hydrogen gas deepens into liquid, then transitions into a metallic state under immense pressure. A small, rocky core, perhaps 10 times the mass of Earth, rests at the planet's heart. Around it, storms and jet streams circle endlessly, their patterns shaped by Saturn's fast rotation. A day on Saturn lasts only about 10.5 hours. The planet's crown, however, is its rings, vast, luminous, and impossibly thin. They stretch over 280,000 kilometers from edge to edge but are, in most places, no thicker than a few dozen meters. Composed mainly of ice and rock fragments ranging in size from grains of dust to mountains, they shimmer as they catch the sunlight, forming one of the most breathtaking sights in the solar system. For centuries, their nature was a mystery. When Galileo first observed them in 1610, his telescope was too primitive to resolve their structure. He described Saturn as a planet with ears. Only later did astronomers understand what they truly were. Countless particles orbiting in perfect synchrony, sculpted by gravity into delicate bands and gaps. But how did they form? Some believe the rings are remnants of a shattered moon, a celestial body torn apart by Saturn's gravity long ago. Others propose they are the leftovers of the planet's formation, a primordial disk of ice that never coalesced. Recent observations from NASA's Cassini spacecraft suggest the rings may be surprisingly young, perhaps only 100 million years old, and that they are gradually eroding, their material falling like icy rain into the planet below. If so, we are living in a rare window of cosmic time, one in which Saturn still wears its luminous halo. Beyond the ring's orbit a retinue of moons, at least 140 known, each with its own character and mystery. Titan, Saturn's largest moon, is bigger than Mercury and shrouded in a dense orange atmosphere. Its surface hides lakes and rivers, not of water, but of liquid methane and ethane. In the dim sunlight, Titan's landscape resembles a frozen mirror of early Earth, an alien world where rain falls from hydrocarbon clouds and rivers carve valleys through icy plains. Beneath Titan's crust, scientists suspect an ocean of water and ammonia, a hidden sea that may harbor the chemistry of life. In 2005, the European Huygens probe descended through Titan's thick atmosphere, capturing images of drainage channels and pebbles shaped by ancient flows. It was the first and only landing beyond the asteroid belt, a glimpse into a world both familiar and strange. And then there is Enceladus, a small, gleaming moon no larger than England, but one of the most extraordinary bodies in the solar system. In 2005, Cassini discovered plumes of ice and vapor erupting from its south pole, jetting hundreds of kilometers into space. Analysis revealed that these geysers contained water, salts, and organic molecules, all the ingredients necessary for life. Beneath Enceladus's icy crust lies a global ocean, warmed by tidal forces from Saturn's gravity. It is possible, perhaps even likely, that beneath that frozen shell, something lives. The Cassini mission transformed Saturn from a distant curiosity into a living system, dynamic, evolving, breathtaking. Over 13 years in orbit, the spacecraft mapped storms that span the planet's poles, witnessed seasonal changes in the atmosphere, and measured the faint vibrations of the rings themselves, which revealed details of Saturn's interior. When its fuel ran out in 2017, Cassini plunged into Saturn's atmosphere, becoming part of the planet it had studied for so long. Its final transmissions, data from its dive through the rings, were a gift to science and a poetic farewell. As it burned up, it sent one last message home. I am here. I am falling. Saturn is, in many ways, the most poetic of planets, a world that embodies both grandeur and impermanence. Its beauty reminds us that even cosmic wonders fade, that everything in the universe, from rings to stars to civilizations, exists for only a moment in time. Beyond Saturn, the solar system grows colder still. The next planets are fainter, their orbits distant and lonely. Yet they, too, hold stories of ice, wind, and the boundary between what is known and what lies beyond. Our next destination, Uranus, the tilted world, the silent enigma. Part 11, Uranus. The tilted enigma at the far edge of naked eye visibility lies a world so strange that even now, centuries after its discovery, it defies easy explanation. Uranus, the seventh planet from the Sun, drifts through the darkness like a pale blue ghost, cold, distant, and eerily serene. Yet beneath its quiet appearance lies one of the most peculiar and mysterious worlds in the solar system. When British astronomer William Herschel first spotted Uranus in 1781, he thought it was a comet. It moved slowly, far beyond Saturn, where no one expected another planet to exist. Its discovery doubled the size of the known solar system overnight, marking humanity's first step into the deep outer frontier. At first glance, Uranus seems unremarkable, a featureless sphere of cyan blue light. Its color comes from methane in its atmosphere, which absorbs red light and scatters blue. But what makes Uranus extraordinary is not its hue, but its orientation. Unlike any other planet, Uranus is tipped on its side. Its axis of rotation is tilted by 98 degrees. It rolls around the sun like a ball rather than spinning like a top. No one knows exactly why. The leading theory suggests a colossal collision in the planet's youth, a glancing blow by an Earth-sized body that knocked Uranus onto its side and possibly stripped away much of its original heat. That ancient catastrophe left a permanent scar in the form of this cosmic tilt, giving Uranus the most bizarre seasons in the solar system. Each pole experiences 42 years of continuous daylight followed by 42 years of night. Imagine a planet where the sun rises once every human lifetime, and then doesn't set again until the next generation. Yet even in that strange rhythm, Uranus remains beautiful. Its atmosphere is composed mostly of hydrogen, helium, and methane, with faint cloud bands and storms that come and go. Beneath the clouds, scientists believe there lies a mantle of icy materials, water, ammonia, and methane, compressed into exotic forms that may behave like liquid metal under immense pressure. Deeper still, a rocky core sits at the center, but what surrounds it defies simple models. Unlike Jupiter and Saturn, Uranus's magnetic field is chaotic, tilted 60 degrees from its axis and offset far from the planet's center. As a result, its magnetic poles wander unpredictably through the sky, and its field flips in intensity as it rotates. It is a planet that refuses symmetry. Only one spacecraft has ever visited Uranus, Voyager 2, in 1986. During its brief flyby, it captured images of a world cloaked in subtle shades of turquoise, accompanied by a faint ring system and a family of moons. For many scientists, those images remain haunting, not because of what they revealed, but because of how much they left unknown. Uranus's rings, though faint compared to Saturn's, are narrow, dark, and composed of icy dust mixed with organic material. They form a quiet, ghostly halo around the planet, the remnants, perhaps, of a shattered moon or ancient collisions. And then there are the moons themselves, 27 in all, each named for characters from the works of Shakespeare and Alexander Pope. Among them are worlds of quiet wonder. Miranda, a fractured moon with cliffs taller than Mount Everest, where ice and rock appear to have been torn apart and refrozen into surreal landscapes. Ariel and Umbriel, with surfaces marked by canyons and strange ridges, evidence of past geological activity. Titania and Oberon, the largest of the group, showing hints of ancient tectonic shifts and dark, carbon-rich plains. Miranda, in particular, stands out, a moon so deformed and complex that it looks like it was shattered and reassembled. Some scientists suspect it was torn apart by tidal forces and later reformed by gravity, a cosmic mosaic stitched back together. In recent years, interest in Uranus has grown again. NASA has identified it as one of the highest priorities for future exploration. A dedicated orbiter and probe mission, currently under discussion, could launch in the 2030s, arriving in the mid-2040s. Its goal: to study Uranus's atmosphere, interior, rings, and moons, to reveal the secrets of this tilted world and the ice giant class it represents. For Uranus and Neptune are gateways, transitional planets between the gas giants and the realm of ice and shadow beyond. They challenge our understanding of how planets form, evolve, and survive. And as we discover more exoplanets orbiting distant stars, we find that worlds like Uranus, cold, dense, and rich in ice, are among the most common in the galaxy. What once seemed strange may, in truth, be ordinary. It is Earth, perhaps, that is the rare one. Beyond Uranus, the solar system grows dimmer still. The sun becomes a distant spark, the stars more numerous, the cold more profound. Yet one last great world waits there, a planet of sapphire storms and unseen depths, the final sentinel before the edge of the dark. Neptune. Part 12, Neptune. The sentinel of the outer dark at the far frontier of sunlight drifts a world of storms. Deep blue, distant, and fierce. Neptune, the eighth and final planet of our solar system, is the last true giant before the darkness of interstellar space. It is the end of the sun's domain, the cold edge of home. Neptune's discovery was a triumph of human intellect rather than sight. In 1846, astronomers Urbain Le Verrier and Johann Galle found it not by accident but by mathematics. The orbit of Uranus showed subtle irregularities, as if tugged by an unseen companion. Le Verrier calculated where that hidden world must be, and when Galle turned his telescope to that patch of sky, there it was. A new planet predicted by equations before it was ever seen. It was the first planet found through the power of human reasoning alone, a testament to our ability to perceive what lies beyond the visible. Neptune is a world of ice and wind, yet its deep cobalt color gives it an ethereal beauty. The methane in its atmosphere absorbs red light, tinting it a more vivid blue than Uranus. But beneath that tranquil hue lies chaos. The fastest winds in the solar system, reaching speeds of over 2,000 kilometers per hour, faster than the speed of sound. How such ferocious winds exist on a planet so far from the sun remains one of astronomy's enduring mysteries. At that distance, sunlight is only 1,000th as strong as it is on Earth. Yet Neptune's atmosphere churns with immense energy, powered perhaps by internal heat radiating from its core. a warmth left over from its violent formation. Like Uranus, Neptune is an ice giant, composed mostly of hydrogen, helium, and compounds such as water, ammonia, and methane. Deep below its clouds, extreme pressure may create something astonishing. Seas of hot ice, water frozen solid yet glowing with heat, or even layers where carbon crystallizes into diamonds, raining down through the mantle in glittering storms. At its heart, Neptune hides a dense, rocky core roughly the size of Earth, enveloped by thousands of kilometers of turbulent fluids. Its magnetic field, like Uranus's, is tilted and offset, producing complex and shifting auroras at its poles. In 1989, Voyager 2 became the only spacecraft to visit Neptune. Its flyby revealed a planet alive with motion, a world not static and frozen, but dynamic and wild. The spacecraft photographed vast storms swirling across the atmosphere, including the Great Dark Spot, a hurricane the size of Earth, with clouds of methane ice drifting in its upper atmosphere. Within just a few years, that storm disappeared, replaced by others. Proof that Neptune's atmosphere is constantly reshaping itself, its tempests forming and dissolving in the cold silence of space. Around the planet, a faint ring system encircles the blue globe, narrow, incomplete arcs of dust and ice, held in place by the gravitational influence of its moons. And orbiting just beyond those rings is one of the most remarkable moons in the solar system, Triton. Triton is no ordinary satellite. It moves backward, orbiting Neptune in the opposite direction of the planet's rotation. This retrograde motion means it did not form with Neptune but was captured long ago, perhaps a wandering body from the Kuiper Belt. Its capture was catastrophic, destabilizing Neptune's early moons and reshaping its system. Today, Triton is a frozen world, but it is far from dead. Voyager 2 revealed active geysers spewing nitrogen gas into the thin atmosphere, proof that internal heat still stirs beneath its crust. The surface, marked by smooth plains and few craters, suggests that Triton has been resurfaced, perhaps by cryovolcanic activity, volcanoes that erupt not lava, but ice. If Europa and Enceladus hint at hidden oceans, Triton confirms that even at the edge of sunlight, geological activity endures. It is possible, though speculative, that beneath its icy crust lies a liquid sea, warmed by tidal flexing from Neptune's gravity. But Triton's fate is already written. Slowly, inexorably, it is spiraling inward. In hundreds of millions of years, it will cross Neptune's Roche limit, torn apart by tidal forces. When that happens, its fragments may spread into space, forming a new system of bright rings, a final halo for the last great planet. Neptune's realm marks the border between the solar system we know and the vast unknown beyond. Beyond its orbit lies the Kuiper Belt, a frozen wilderness of ancient remnants, where dwarf planets like Pluto, Haumea, and Eris drift through the dark. These icy worlds, small and distant, preserve the raw materials from which the planets were born. They are fossils of creation, whispering secrets of the time before light. To look upon Neptune is to gaze into that frontier, the place where our sun's influence fades and the stars begin to rule. Here, at the edge of the solar system, one realizes the scale of what we have built, seen, and understood. From the fiery heart of the sun to this distant blue sentinel, humanity has traced the arc of its cosmic home, a journey billions of kilometers long, powered only by curiosity. And yet, even here, at the boundary of the known, one truth persists. The universe does not end. It only begins again. Beyond Neptune lies silence, and beyond silence, the infinite. Would you like me to continue with part 13, the edge of the sun, the Kuiper Belt, and the Oort cloud? Part 13, the edge of the sun, the Kuiper Belt and the Oort cloud beyond Neptune. The familiar architecture of the solar system begins to dissolve. The great planets end, and the sun's light fades into the cosmic dusk. Here, at the edge of our stellar neighborhood, lies a vast and silent frontier, the Kuiper Belt, a realm of frozen debris, ancient survivors from the dawn of creation. This is no empty space. It is a colossal ring, extending billions of kilometers beyond Neptune's orbit, filled with icy bodies that never grew large enough to become planets. These remnants are the leftovers of the solar system's formation, the raw materials that once swirled around the newborn sun, preserved in the deep freeze of distance. Among them drift worlds that defy simplicity. The first and most famous is Pluto, once hailed as the ninth planet, now reclassified as a dwarf planet. Discovered in 1930 by Clyde Tombaugh, Pluto captured the imagination of generations. For decades, it was little more than a faint point of light, its surface unknown. Then, in 2015, NASA's New Horizons spacecraft flew past, revealing a world far more complex than anyone expected. What it found was astonishing. Pluto is not dead or inert, but alive with geological activity. Its surface is carved by nitrogen glaciers, its plains reshaped by slow flows of ice that behave like rock. A heart-shaped region, Tombaugh Regio, stretches across one hemisphere, a vast expanse of frozen nitrogen bordered by dark highlands of methane ice. Beneath that frozen crust, there may even be a subsurface ocean, kept liquid by heat from radioactive decay. For a world so small, barely 2/3 the size of Earth's moon, Pluto has proven unexpectedly dynamic. It even has an atmosphere, tenuous and delicate, composed of nitrogen, methane, and carbon monoxide that freezes and thaws with the seasons. As it nears the sun, gases evaporate from its surface, forming a thin blue haze. As it drifts away, those gases fall again as snow. Orbiting alongside Pluto are 5 moons, the largest of which, Charon, is nearly half its size. The two are locked in a gravitational embrace, circling a point in space between them, a double world. Charon's surface is scarred by vast chasms, one stretching more than 1,000 kilometers long, as if the moon once split and refroze. Together, Pluto and Charon dance at the threshold between planet and space debris, between past and present. Beyond Pluto, the Kuiper Belt continues, home to a growing catalog of dwarf planets. Haumea, a rapidly spinning oval world with icy rings. Makemake, bright and methane-rich. Eris, once considered larger than Pluto and the spark of the planet debate. Each tells a story of formation and survival in the cold outer dark. But even the Kuiper Belt is not the end. Far beyond it, at distances so immense that the sun becomes just another star, lies the Oort cloud, a vast, spherical shell of icy bodies surrounding the entire solar system. It is a region so distant that no spacecraft has ever approached it, and no telescope can see it directly. Yet its presence is known through the messengers it sends. Comets. When gravitational nudges, perhaps from passing stars, disturb these ancient objects, they begin their long fall toward the sun, shedding gas and dust as they near the warmth. Their glowing tails and brilliant comas are the whispers of the Oort cloud, reminders that even in the coldest corners of space, motion and change never cease. Some of those comets, like Halley's, return in predictable cycles, their orbits carved by the sun's gravity. Others visit only once in millions of years, their paths hyperbolic and unbound, slingshotting through the inner solar system before vanishing forever into interstellar night. The Oort cloud may extend up to a light year from the sun, halfway to the nearest stars. It marks the boundary where our solar system ends and interstellar space begins, where the sun's gravity finally releases its hold. It is here that our story, the story of the solar system, meets the universe beyond. Every planet, every moon, every icy shard within this cosmic bubble owes its existence to that one central star. Yet beyond the Oort cloud, the sun becomes insignificant. Its light fades, its warmth dies, and the galaxy takes over. Stars drift in the distance, each with its own planets, its own histories, its own stories of creation and loss. In the vastness of that scale, our solar system is a grain of dust, and yet, within it, life arose, looked outward, and began to understand. When Voyager 1 crossed the boundary known as the heliopause in 2012, it became the first human-made object to enter interstellar space. Even now, decades after launch, it continues to send faint signals home, messages carried on waves of radio light, across distances so vast that each reply takes more than 40 hours to arrive. On its side, attached like a cosmic time capsule, is the Golden Record, a collection of sounds, images, and greetings from Earth. A message to whoever might one day find it. A record of who we were and what we hope to become. It carries no destination, only direction. If ever it is found, it will be by beings who have never seen our sun, who may live beneath skies we cannot imagine. They will not know us, but they will hear our voice, the echo of a species that dared to reach beyond its cradle and name the stars. At the edge of the sun's light, among the drifting ice and shadows, that record sails onward. Humanity's whisper to the infinite. Part 14, The Messengers. Voyager, Pioneer, and the legacy of exploration long before we dreamed of leaving the solar system. We built emissaries to carry our curiosity outward. Silent explorers made of metal and code, sent into the great unknown with no promise of return. They were called Pioneer and Voyager, and though they have long since passed beyond the reach of planets, they remain humanity's most enduring footprints in the cosmos. Their story is one of courage, precision, and wonder, the first attempt by our species to speak across the void. The Pioneer 10 and Pioneer 11 spacecraft launched in the early 1970s, becoming the first to travel through the asteroid belt and to approach Jupiter and Saturn. They were simple by today's standards, weighing barely 250 kilograms, powered by small nuclear batteries, but their missions rewrote the map of the solar system. Pioneer 10 was the first human-made object to leave Earth's neighborhood and head into deep space. It captured humanity's first close-up images of Jupiter, revealing its vast magnetic field and radiation belts. A few years later, Pioneer 11 followed, venturing even farther, flying past Saturn and sending home our first glimpses of its majestic rings. Both carried something profoundly symbolic, a gold anodized plaque engraved with a map of the solar system, the silhouette of a man and woman, and a line showing the trajectory from Earth into the stars. It was humanity's introduction, a cosmic calling card for whoever might one day find them. Then came Voyager. In 1977, two nearly identical spacecraft, Voyager 1 and Voyager 2, embarked on what NASA called the Grand Tour, a rare alignment of the outer planets that occurs only once every 176 years. Their mission was audacious: to visit Jupiter, Saturn, Uranus, and Neptune in a single sweep, a journey spanning billions of kilometers. The success of Voyager redefined exploration. At Jupiter, Voyager revealed a planet alive with energy, lightning storms, turbulent clouds, and the volcanic fury of Io, the most geologically active body in the solar system. At Saturn, it captured the exquisite structure of the rings, the hazy orange shroud of Titan, and the serene beauty of the planet's storms. Voyager 2, continuing onward, became the first and only spacecraft to visit Uranus and Neptune. It found Uranus tipped on its side and shrouded in icy blue clouds. Neptune, darker and stormier, with winds faster than any on Earth. It completed humanity's first complete tour of the solar system, a journey that no other mission has yet repeated. But the Voyagers carried something more than instruments and cameras. Each was equipped with a golden record, designed by a team led by astronomer Carl Sagan. Etched in gold and sealed in aluminum, the record contains the sounds and images of Earth. Greetings in 55 languages, music from Bach to Chuck Berry, the laughter of children, the roar of thunder, and the sound of a mother kissing her baby. On its surface is inscribed a map, showing how to find our sun, how to decode the sounds, how to know who we are. It is, in every sense, a message of hope. The Voyagers continued their missions long after they left the planets behind. They discovered the structure of the heliosphere, the vast bubble of charged particles blown by the solar wind, and eventually crossed its boundary into interstellar space. In 2012, Voyager 1 became the first human-made object to do so, moving beyond the influence of our sun's solar wind. Voyager 2 followed in 2018, confirming that it, too, had entered the space between the stars. Even now, decades later, their faint radio signals continue to reach Earth. Each photon of that signal travels for over 22 hours before arriving at NASA's Deep Space Network antennas. The information they carry, temperature, magnetic field strength, cosmic ray data, is meager yet priceless. These two small machines, built in the 1970s, are now the farthest human creations in existence. Their power is fading. Their instruments are shutting down one by one to conserve energy. Within the next decade, their voices will fall silent forever. Yet even then, they will continue to drift, endless travelers carrying our signature. In a billion years, they will still be out there, long after Earth's continents have shifted and the sun has changed. If ever they are found, they will tell whoever discovers them that once, long ago, a species on a small blue world looked up and wondered. The legacy of Pioneer and Voyager endures not just in space, but in spirit. They inspired every mission that followed: Galileo, Cassini, New Horizons, James Webb, and those yet to come. They taught us that exploration is not about conquest, but about connection, the act of reaching outward to understand what lies beyond ourselves. Today, as we prepare to send new probes to Jupiter's moons, to return samples from Mars, and to launch telescopes capable of seeing the first galaxies, we are continuing the work Voyager began. The technology has changed, but the question has not. Are we alone? That question is written into every line of data, every image, every echo sent home across the void. And though the Voyagers will one day fall silent, their message will continue, a golden whisper sailing between the stars. The journey, however, does not end there. Beyond the reach of even those messengers lies a boundary not of space, but of understanding, the edge of what we can yet imagine. The next chapter is not about where we have been, but where we might go. Beyond the solar system, beyond the known, toward the infinite. Part 15, Beyond the Sun. The future of exploration and the question of life. The story of the solar system does not end at its edge. It merely opens into a greater one, a story not of planets or stars, but of a species that refuses to stop asking questions. Humanity has reached the outermost boundaries of its home system, yet our gaze stretches farther still, toward new worlds circling other suns. The future of exploration is no longer confined to the solar system. It is cosmic. For thousands of years, our ancestors looked to the sky and wondered if we were alone. Now, for the first time, we have the tools to begin answering that question. The discovery of exoplanets, worlds orbiting distant stars, has transformed astronomy from a study of our local neighborhood into a survey of the galaxy itself. In 1995, the first confirmed exoplanet around a sun-like star, 51 Pegasi b, shattered our assumptions. It was a hot Jupiter, a gas giant orbiting so close to its star that its year lasted just 4 days. Since then, space telescopes like Kepler, TESS, and now James Webb have revealed thousands of worlds, some scorched, some frozen, some eerily Earth-like. Among them are planets in the habitable zone, where temperatures may allow liquid water to exist. Some orbit small, red dwarf stars, others circle suns much like our own. With every discovery, the line between fiction and reality blurs. The universe, once thought barren, is now known to be abundant. And yet, abundance is not the same as life. To find life, we must listen, in light, in chemistry, in silence. The James Webb Space Telescope is already peering into alien atmospheres, searching for biosignatures, traces of oxygen, methane, and carbon dioxide in balance, chemical fingerprints that could suggest living processes. These signals are faint, fragile, whispers across light years, but they remind us that biology may not be unique to Earth. Closer to home, the search continues on familiar ground. On Mars, the Perseverance rover collects samples that may one day prove whether life once thrived in its ancient riverbeds. On Europa and Enceladus, probes are being designed to dive into subsurface oceans where heat and chemistry may sustain alien ecosystems. And in the golden clouds of Venus, scientists still debate whether traces of phosphine gas could hint at something surviving high above the inferno. These worlds, once imagined as lifeless, have become laboratories of possibility. But exploration is not only about finding life. It is also about ensuring our own continues. Humanity stands at the threshold of becoming a multiplanetary species. Space agencies and private ventures alike plan missions to establish outposts on the Moon and Mars within the coming decades. These first colonies will be fragile, dependent on Earth for supplies, but they will mark the beginning of something profound, the extension of life beyond its birthplace. The challenges will be immense. Radiation, isolation, gravity, and time will test every limit of human endurance. Yet history shows that curiosity is stronger than fear. Every step forward, from the caves of prehistory to the plains of Mars, has been driven by the same question: what lies beyond? Beyond the drive for survival, there is also the search for meaning. Exploration reminds us of our unity, that we are all passengers on the same small world, orbiting the same star. The image of Earth as a pale blue dot, captured by Voyager 1, remains our greatest lesson in humility. It shows us how small we are and how precious. The future will carry that lesson outward. New probes will sail to the icy moons of Jupiter and Saturn. New telescopes will look for habitable worlds beyond the Milky Way, and new generations will grow up knowing that the night sky is not a ceiling, but a map. And perhaps one day those maps will lead us to others, civilizations that have looked upon their own suns and asked the same questions we do now. If we ever meet them, it will not be as conquerors or strangers, but as kindred explorers in an infinite ocean. Until then, our journey continues, a thread of light stretching from the sun into eternity. In a few billion years, our star will fade. The Earth will change. The oceans will boil away. The continents will crumble. And the sun will expand into a red giant before collapsing into a white ember. The solar system will drift into darkness. But by then, perhaps humanity or its descendants will have already spread to the stars, carrying with them the legacy of this place. Every spacecraft, every telescope, every heartbeat of discovery is a message to the cosmos. We were here. We looked outward. We understood. And so, as we stand beneath the same stars that guided the first watchers millennia ago, we return to the question that has echoed through every age. From Babylon to Voyager, from Mercury to Neptune, from Earth to eternity.